So this lecture is the last part of chapter 14, and in this final subtopic we're going to talk about, or continue talking about, glaciers and some ideas about how we define mountain glaciers from continental glaciers and some different aspects of these, and finally to talk about cycles, so glacial interglacial cycles, and what is driving this particular cyclical nature of moving from ice ages to periods where we have no ice age. Firstly, to look at mountain glaciers, and here we've got some different examples of aspects or landscape features of mountain glaciers. So we see some glaciers here moving down valley, and these are of course called mountain glaciers because they're forming on mountains or high mountainous regions. And they are also sometimes referred to as valley glaciers, that occupy valleys and carve these features out as they move down to lower elevations. We can also have snowfields, so this is a number of glacial systems all coalesced at high elevation, which then have a number of glacial tongues which move down from the snowfield in different valleys, as we see here. This is an example from Alaska. We mentioned moraines last time in the last lecture, but here we've got a moraine. Okay, so this is the material that builds up both to the sides here of the glacier in these areas of what looks like grey debris, and also in the foreground where we're getting meltwater outwash, as well as dumping of big deposits of sediment in these moraines. And the final slide here is indicating the terminus. So this is the lowest elevation that the glacier reaches, and in this example here we've got ice and also debris covered ice in this terminus. So this is the lowest extent, the lowest elevation of the glacier, where it's producing a terminal moraine. So all this material here is the glacial till, the sediment deposited by the glacier in its terminal moraine. And then we see, as we move further down valley, this meltwater channel. Okay, so we've got meltwater, it's where it's melting, being ablated and taking with it further sediment away from the glacial system. Some further landscape features of mountain glaciers, and this also kind of like goes a little bit further from the previous lecture when we were talking about evidence of glaciers in the landscape as well. The first of these is the cirque, and perhaps this line here should be indicating a bit further up into this bowl shape. A cirque is a bowl shape at the top or the highest elevation of the glacier here, and this sort of feature forms by the ice freezing onto the rock walls and plucking out chunks of rock and forming this bowl type depression. And it's slightly lower in elevation. We've got a sort of slight lip here, and so the bottom of the cirque is quite often occupied by lakes, as we see here, when a glacier has completely melted out and removed, and we've got water moving down valley from this lake as well. In the photograph here, of course, we've got a cirque which is full of snow and ice here. Another common feature are known as arêtes, and these are these very sharp, jagged rock formations at, again, the top of the glacial system, and these form due to glaciers forming either side of rock formations and producing as a result very jagged rocks such as these. Okay, so we've got some examples, of course, in our reconstruction here as well. Another common feature that we see are known as hanging valleys, and in this example we've got a glacier that's moved down in the main valley here and has eroded out and carved out a very large and deep valley. Then in this smaller and higher valley we've got another small glacier that was present, and it's left this valley hanging. Okay, so when this main glacier has carved out this much larger valley going kind of like this way, it's left this valley hanging in this way. And again, these are quite commonly occupied by lakes, just as the main valley is occupied by a lake or a fjord, and quite often see waterfalls, so they're quite spectacular areas where we have one of these hanging valleys. The last photograph in this sequence of landscape features are the moraines themselves, and we actually have two glacial systems which have met further up valley here and have come down this valley together and have produced a set of different moraines. We've got a medial moraine, and the reason we have a medial moraine, M here, is because of these two glaciers coming down side by side and producing or depositing sediment in the middle moraine or the medial moraine here. And then we have lateral moraines, and this would be typical even if there was only one glacier coming down this valley. It would have lateral moraines to either side of the valley as the glacier comes down and deposits material. At the end, again, another example of the lowest extent of the moraine, where we've got this large terminus T here, the large terminal moraine. If we consider now landscape features of continental ice sheets, well, the first main thing we have here are the ice sheets themselves, and these are the transantarctic mountains that we see in this ice sheet. So these are large mountains which are popping up above this thick ice sheet that's covering Antarctica. Other features of continental ice sheets, we also have polished bedrock and or polished surfaces, as we show in this slide, and also glacial till. And also the margins, so where ice sheets do meet the sea. And again, of course, this is another example of the Antarctic ice sheet. We have an ice shelf. So some landscape features, and we've got various features here of a continental ice sheet, similar to the mountain glaciers or valley glaciers. We've got the furthest extent over which the ice sheet moved across the land and left a terminal moraine here at the end. We also see a number of recessional moraines, and these are indications of where the ice has moved back and then stopped and dumped more material as a recessional moraine, and then moved back again and done the same thing again. Okay, so produced a sequence of these, but again this is the furthest extent in terms of the terminal moraine here. We also got sedimentary deposits which have been shaped with the direction of the ice, and these are known as drumlins in terms of these features that we show here, which are pretty much perpendicular to the ice at the front, or the front part of the ice sheet here. Eskers are channels beneath the ice. We talked a little bit about these already, but this would be streams running beneath the whole ice sheet, which are subsequently choked with sediment and form these sinuous esker formations, and they have S-like shapes, just as the channels, when they're sort of meandering around beneath the ice, have these shapes as well. And we've also got a large area, and typically a large area when we see these outwash areas, so glacial outwash areas of sediment, and we've got meltwater channels here which move around and produce a large area of sediment. Kettle lakes here. Kettle lakes are formed by, again, chunks of ice or blocks of ice that break off the front of the ice sheet, and when these features eventually melt, they produce small lakes. And again, all these sorts of features are all left behind in the geologic record when there's of course no ice sheet present, so they're very useful ways of studying past glaciation, finding evidence for past glaciation. Here we've got some eskers in the photograph here. These are from Iceland, but we see quite nicely how we've got these snake-like features of all this sediment which has filled the channels which were beneath the ice sheet. Okay, so on to cycles, and the last sort of parts of this glacial subtopic are related to glacial cycles, or glacial and interglacial periods, and this is all related to how the sun affects the earth, or the relationship between the sun and the earth, and how that has changed or changes over time. And the first of these cycles is, as it says down here, a 40,000 year cycle, and this is related to how the earth tilts or changes its tilt with respect to the sun. So if we imagine the sun's rays coming in pretty much parallel to our dotted line here through the earth, we see that we have a tilt in this particular time of maximum tilt of about 24.5 degrees, moving through to 23.5 degrees, and then the minimum tilt of 22.5 degrees. And so the earth moves through this whole tilt with respect to the sun over a 40,000 year cycle, and this affects the solar heating of the earth, and affects whether there's colder times or warmer times, and so also affects how much ice can be retained at the poles as a consequence. So if we put a little bit more text on here, if we have a larger tilt, we get more seasonality. With a larger tilt, we get more seasonality, with maximum tilt, there are warmer summers near the poles and less glaciation. Okay, so we've got to think about, well, the Earth being with respect to the Sun both sides, so it's at maximum tilt, warmer summers and less glaciation. 23.5 degrees is near to the present day tilt. It's actually currently adjusting back from the maximum, so we're at maximum tilt, which coincides with similar times of the last glaciation. And if we consider minimum tilt, we actually have cooler summers, so there's less effect of the Sun in the polar regions, for example, and therefore more solid ice can be retained there. So two further factors, again with a similar discussion, again this relationship of the Earth to the Sun, to solar heating. And the first one here is how the Earth precesses. We see we've got a kind of wobble, a precession between the North Star here and Vega, and this precession occurs over a 23,000 year cycle. Okay, so we've got another cycle which is imprinted on the 40,000 year cycle that we've just discussed, and a further one which is to do with how the shape of Earth's orbit changes on a 100,000 year cycle with respect to the Sun, and we see how the orbit moves from being less eccentric, so more circular, let's say, to more eccentric and more oval. And when it's more oval, of course, the Earth at times has further distance from the Sun. Okay, so this again affects the amount of solar heating, and this overall cycle is eccentricity. So we've got the wobble of rotation axis, or the precession on a 23,000 year cycle, and the shape of the orbit, or eccentricity, on a 100,000 year cycle. Last slide to consider, chapter 14, are aspects again, but closer to the surface, or at the surface, in terms of the Sun's relationship and the Earth. So we're talking about overall global and perhaps also local effects in terms of warming and cooling, and some of these ideas we've mentioned before. The first of these is if we have an increase in sunspot activity, and that's has an overall warming effect. The second is an increase in reflectivity, or albedo, what's known as albedo, from snow or clouds, and that has a cooling effect. Well, this is sort of a feedback mechanism, because if we're already moving into a cooler period with more snow and ice on the surface of the Earth, and more cooler, cloudy weather, then we're going to have more albedo, and therefore more cooling as a result, and more reflectivity, and not so much of the Sun's energy reaching the Earth. The last two here are examples that we've talked about before, related to volcanic activity. So we've mentioned quite a few times now in the geologic past how we've had very immense volcanic activity, particularly from flood basalts, and we see here that we can have gases which are related to greenhouse effects such as CO2, and produce overall warming. And we've then got the example of volcanic ash in the atmosphere as a result, and this is kind of like an opposite effect, so it's sort of balancing out, equaling out to a certain degree greenhouse effect. but volcanic ash and dust causing reflection of solar radiation and overall cooling.